So, domain-specific tensor languages is the only thing that keeps you from lunch. Yeah. Tensor calculus in this setting is not what they talked about in the previous slide. It's something from 100 years ago. It's not TensorFlow, it's tensor calculus. So the thing that Einstein had to learn from mathematician friends to be able to express the curvature of space-time. And an example is this Riemann curvature tensor here. It's a symbol with some upper and lower indices, and it's defined as this 4-term expression which uses derivatives and Christoffel symbols, which are in turn implemented in terms of derivatives and the metric, which is also a 4-term expression. So it's a big, annoying expression. And we will we have implemented 2 tensor DSLs embedded in Haskell, conversions between them and helper functions to then view these tensors in the Einstein index notation or as diagrams. And sort of one minute version of the talk, if you're impatient, is this. So we have this Albert after Einstein and Roger after Penrose languages embedded in Haskell. And as a very small example, the Albert function example of t and u is a contraction of this lambda expression. And here I've abused Unicode a bit. So this is an upper I and this is a lower I. These are 2 different variables bound by the lambda. I write low I and high I in the actual code, but render it this way. And then t is applied to one of the i's, deriv is applied to the other I and to u. And then we will look at later what this might mean. This is the kind of expression you write in Albert. And this can render itself then as the index notation, well, which is slightly shorter. The contraction here is sort of invisible, but the fact that an index is used twice, there is a convention in the Einstein index notation that if it's used up and below, then it means the summation, so that's the contraction. It can also render itself as a diagram. We will get back to the meaning of those diagrams later, but you can see that at least the t is connected to u in some way here. And you can otherwise run it on matrix representations of these tensors and get actual computation results, even though we only use symbolic expressions and real numbers in the examples we've done so far. In the paper, the sort of motivating example is to express the general relativity equation for the curvature of space-time, which is this equation actually, using this curvature tensor, the metric, and the energy matter, sort of energy momentum tensor. We'll not talk much about that, but a little example at the end. So the 5-minute version of the talk is the core contribution, is this implementation. 2 DSLs, as I mentioned, Roger after Penrose, is based then on symmetric monoidal categories. And the other one is based on linear functions between ports. And this is now, even though tensors are about linear algebra, this is type linear functions between ports. So it's not about, so there are 2 ways the word linear appears in this paper and this talk. One is as type linear functions, where you can use the argument, where you have to use the argument exactly once, and the other is when you have linear transformations. And the types we'll get into later, but you can see that tensor embed is a function that goes from this, which is actually Roger, and to the other thing, which is an expression in Albert. So you can get from one to the other and back, and we'll get to the exact types later. Okay, so there are 2 main lessons learned if you want to sort of condense. So one is that you can use both a point-free calculus and lambda expressions. That's what these 2 views are. And why is this relevant? Well, point-free calculations are algebraically nice. You can do calculational proofs and so on, but try to do plumbing of variables when you have more than 2 or 3 involved. That's going to be very awkward to work without variables. On the other end, if you have lambda expressions, you can easily connect computations, name and reuse different sub-expressions and so on, well, implemented as ports here. But reasoning is always harder with name binding and so on. So as I said, we provide both, and it allows you to mix and match in the sense that you can have sub-expressions which are in Roger in an expression using Albert and the opposite. And it means that certain expressions can be more conveniently expressed. And then the underlying technique here is what was published in 2011 and based on a well-known isomorphism between symmetric monoidal categories and linear lambda calculus. Well, it wasn't well known for me when I started this work, but apparently it's well known. And this is the sort of nice underlying theory saying that if you have an arrow from A to B in some category Z, which is symmetric monoidal, you can translate that into a polymorphic function between a port of type A to a port of type B, and this is the linear function arrow. And this squiggly arrow is only for formatting. ZAB is what it would say in Haskell. So Z is a two-parameter type constructor applied to A and B. And then the decode function is the opposite direction. It just takes one of these polymorphic functions and goes back. You can think of the R here as a scoping construct handling, a bit like the ST monad in Haskell and so on. And this paper adds several things, but when it comes to this technique, it's mainly adding a little more structure on the category side to get compact closed and additive categories. And then we encode such an arrow not as a function just from port of A to port of B, but we require the compact closed, meaning that you can sort of turn inputs to outputs, which hints at like quantum computing and so on. So the B star here, which is written dual B in the Haskell code, is the sort of way of making an input and output or the opposite. So then you take an input, you take an output, and you return some results. And similarly, the two functions are inverses here as well. So if you have such a polymorphic function, you can make it an arrow. Okay, that was the 5-minute version of the talk. Let's continue with lesson 2. Building a DSL with type classes is a useful technique, and I'm sure most have used this in different languages. So if you take a very simple example, if you want to write a numeric expression, like lit foo, for example, it's x plus x times y, and it has type num A constrained A to A to A. So for any type A, could be integers or floats or polynomials or some other mathematical type, you could have this as sort of your interface for a numeric expression DSL. And basically these expressions are then, if you just use these class methods, you get generic numeric expressions we could later instantiate to different types. And that's how we build up Roger, but it has a little more structure to it. So we start from the category type class, not our invention at all. We add symmetric monoidal operators. I will show types on the next slide. We require these, the Hom set of this category to be additive, so you can add morphisms and scale them. And then we require it to be compact closed, so you can sort of take an arrow and turn it around in the other direction. And the expressions using only these operations are then Roger expressions, and those are the ones which can be translated into the linear lambda calculus version. Of course, if this would be an empty set of requirements, they would be very useless, but we have a few instances, like for matrices, diagrams, and pretty printing. So expanding a bit, the actual interface declarations for the class category, it's, again, as I mentioned, Z here in Haskell would be just written prefix, so ZAA, ZBC, ZAB, and ZAC. That's identity and composition. So the whole Roger language is a way of describing morphisms in some category. And the symmetric monoidal has, in addition to these operators, 5, 6 more. So tensor product is the most important one, where you basically put two wires in parallel, or two computations, two arrows in parallel. And then you can do some swapping, associations, and so on. And I mentioned additive, basically saying that we require the arrows, the Hom sets, to be additive, to have addition and scaling and a 0. So that's the structure. And I talked about diagrams. These are the key operators and how they are rendered. It's a bit fun because Jean-Philippe is really a Tesh and Haskell and everything hacker, so he implemented this thing. So the paper and the talk generates this figures this automatically. So this syntax generates this, and this is generated from the type of this. I maybe specialize it to a monomorphic type just to illustrate. So composition, well, in the diagram form, it's pretty clear. You take some input port I, you thread it through T and U and go to J. Well, actually, what is input and what is output is not that important because you can then dualize it. The Einstein notation version has I and J as indices, but then also a K. And the fact that it appears both below and above means that it's implicitly summed over. So there's actually a contraction happening here. That's a sigma K over this. So it only has two free variables, and the third K is a bound variable. This is not Haskell notation. This is the Haskell notation or the Roger notation. The tensor product is, as I said before, running two computations in parallel. So I and J are inputs, K and L are the output ports, and T and U are sort of run independently here. Sigma, the swap, well, you just cross the wires, and associators, alpha, they take I and J close together here to M and N close together there. So it's sort of implementing associativity. And you can imagine if you want to have a large wire diagram, like something from the keynote talk, it would be very inconvenient to write it in Roger, but you can generate that from the lambda expression version. Okay, getting slightly more concrete, how do we implement this vector space part in Haskell, where we have first an additive group, addition, zero, and negation, and then we add the scaling operator. So it's an infix operator taking a scalar on the left and a vector, and then scaling it up or down, or flipping it if it's negative. We haven't parameterized it on the type of scalars, but that could also be done. So S is some type, for example, real numbers. So if you want to be extra concrete, you could say S is real numbers, V is capital V being a two-dimensional vector space with some basis vector, and as you know from linear algebra, we can then write any vector as some real number V1 scaling E1 plus some real number V2 scaling E2. So it means also if we later we can have a basis for the tensors, and we can write linear combinations of tensor expressions. So the category that's at least symbolically intended is the category of finite dimensional vector spaces as objects, and linear transformations between them as arrows or morphisms. And these arrows are the tensors. So tensors are linear transformations between vector spaces, or often described as linear transformations between tensor products of vector spaces. So to be a little more concrete, the types here, A and B and C and so on, they are representing the index set of the basis. So if it's the unit type, it's a one-dimensional vector space. So there is just one index vector. And what is that vector? Well, you usually call it 1. So the real numbers is a one-dimensional vector space over the real numbers. So any vector in that vector space can be written as a scalar times 1. A two-dimensional space we had in the previous slide, and if you want an example of a linear transformation, then we can take rotation by 90 degrees, and it can be represented as a matrix. Well, this I can just show quickly. If you have a vector space, you can also make a vector space of functions. You just lift everything and work on the return side. And then we can get the simplest examples of actual tensors. So as I mentioned, if you have the unit type, then it's basically real numbers. So what is a linear function from a real number to a real number? Well, linear function here means really linear algebra linear, so it's just multiply by a constant. So you can determine a scalar is isomorphic to a linear function from the one-dimensional to the one-dimensional space. And then a vector is 1 to v. A vector ether, a covector, is something from v to 1, and then a normal matrix or linear transformation would be v to v. These are usually described as tensors of order 0, 0, so 0 for the input, 0 for the output, 0, 1, 1, 0, and 1, 1. And you may notice this order here is a pair of you could say, the exponent of v on the left and the right. So how many v's are tensored together. So generally speaking, a tensor is usually v to the m arrow v to the n of order mn. So you can have like 3 things on the left and 5 things on the right if you want. And you can informally think of it as taking m vectors as inputs and producing n vectors as outputs. But it's not quite that, because that would indicate you have a Cartesian product. So you have like really the different vectors in your hand. But tensor product doesn't quite work that way. So if you have a basis for v and a basis for w, say 2-dimensional and 3-dimensional vector space, then the basis for the Cartesian product would be 6-dimensional, 2 times 3, while the Cartesian product would be the sum, 2 plus 3, a 5-dimensional space. So you can also do the tensor product on the value level. So you can take 2 vectors or 2 tensors and tensor them together. It's a little bit like a pair, but you can move constants between them. So if you have a constant scaled v tensor w, it's the same as v tensor c scale w. That means that if you tensor 2 things together, you can't get the vectors back out again. They've sort of been entangled together here. And it's a bit like multiplication, of course. If you have a times b and multiply them up, you can't get a and b back again. You have a little more information than that because of the basis, but you don't know the scaling factors. I don't have time for the details. So in the paper, the second half of the paper is about going from what I've talked about so far, which is basically tensor algebra, to tensor calculus, when things are varying in some space, in some manifold. So for example, then the basis will also have to vary based on position. So here is an illustration of a Cartesian basis. So this 2-dimensional space, it always looks the same, but if you have the polar system, then you have little base vectors which change by position. And the use of this in physics is usually using partial derivatives, and then you need a kind of derivative that would work with tensors, and it has this type here. So if you have any tensor, arrow from A to B, it will give a tensor with one more sort of argument, one more input. And you can see that's a directional derivative in that extra argument. And this is just for the teaser for the paper. This is what the general relativity curve space-time equation looks like. Remember that R was defined as 4 different terms using derivatives and Christoffel symbols, which in turns have an expression using a few terms, using more derivatives and metric tensors. So everything is a big, complicated sum of derivatives of different sub-expressions, and everything boils down to how the sort of energy momentum tensor is translated to the curvature of space-time, which is the metric tensor G. So G is actually the variable you solve for. The tensor field G is what you want to compute from knowing a matter distribution in the universe. This was just showing the diagram version of the curvature tensor. So in the paper, we don't solve this. I mean, it was solved by Schwarzschild in the same year as Einstein published the equations. But the sort of cute thing with it is that the solution has this strange behavior. So I could say just in 1 minute, it's a universe with spherical perfect symmetry and 1 point mass. So the simplest case, you want to solve something simple. You start with 1 point mass, and then everything else is empty space. And then it turns out that you get this strange behavior like a black hole thing, that there is a radius inside of which nothing can escape. And why is that a black hole, just a 1 point mass? Because the point mass has infinite density. So regardless of how little mass you got there will be some little radius around it which will be where it behaves like a black hole. So there was sort of, in some sense, theoretical discovery of the black hole 100 years ago. This is what I said in the beginning, basically, contributions to domain-specific embedded languages. You can express these notations. If you do this particular expression, it means T is a vector field, U is a scalar field, and this expression is the directional derivative of U in the direction of T. So if T is the wind field over the Earth. U is the temperature. It's the rate of change of the temperature in the direction of the wind. In the paper, there's more stuff, and yeah, please, questions. I don't think it works. Maybe you can.
When it comes to the tensor product, did you consider, so there's a few ways you can think of maybe representing the language. One, which we see in things like tensor in your work, is the kind of categorical approach to it. The other is maybe identify the universal property. Have you considered like different ways it can be encoded as axioms?
Well, I mean, as this is sort of, there's an abstract syntax tree of this in the background and so on. It's sort of it's axiomatic in some sense, you could say, and we don't really use any specific properties. I mean, it has to be a symmetrical monoidal category for the transformations to work, but I don't think we represent tensor product in a specific way. I mean, the way we define it in the paper is by the universal property. Yes. Yeah. No.
Second question, are there tangent spaces?
Well, we don't have specific expressions for them, but I mean, they are there.
Thanks for the talk. I really enjoyed it. I guess, so the question that I had was, so like it wasn't really clear to me whether the only expressions, so the thing that wasn't clear to me is whether like the only expressions that you can write down are those that, transform like a tensor, or whether you can also write down, like for example, like it seems that you can write down Christoffel symbols, which are themselves tensorial, right?
Yeah.
So like somehow, yes. Right, but in some sense, like in the language, you do have a way to go from, like the non-index notation to the index notation. So like, what actually happens if I write down something that is in itself not non-tensorial, and I then say, please give me like, like the index-free version of it, and then I come back. Like, does it really?
So we have a class for the partial derivative operations, which is sort of impure.
Okay.
It's not. It doesn't sort of satisfy the tensorial laws.
Sure. And then from that you build the covariant derivative.
Yeah, we implement the Christoffel symbols, and then we have to prove then that something is actually a tensor. I don't think the translation, because the translation isomorphism depends only on the underlying symmetric monoidal category representation. So that will, well, I guess maybe it just fails if it turns out not to be a tensor. I haven't tried.
Okay, yeah.
But it would be interesting to explore, yes.
Yeah, thank you. Yeah.
Hi, thanks for the great talk. I was curious if you have any particular opinions or insights into what you are getting in your particular encoding from introducing covariance and contravariance, which is sort of, I would think of as the main, the upper and lower index, compared to the previous talk, and just think of, well, whatever, a tensor is an array of numbers. I know conceptually for physics it's very important, but do we have practical payoffs in introducing that into languages? Can we articulate what those are for people?
Well, this duality between inputs and outputs is what, as we use, how should I put it? One of the main motivations here was to be able to code up and give type errors for things which are not right according to the Einstein notations. So if you don't keep track of the upper and lower indices, you will be able to write sort of nonsensical expressions. In many cases, as there are lifting and lowering operators, you could sort of guess that, oh, they probably meant this, and then lower one or raise the other one. But then there would be this unclarity of what you actually meant. So we haven't implemented any sort of automatic inference of the index positions. I'm not sure if that answers the question.
I don't know. I mean it as a friendly question. I think it's an interesting it would be great if we have a really clear answer to that.
Well,
for
I would
people.
say then usually in tensor computations, you don't change the basis. I mean, in the sense of TensorFlow, you just have this thing.
Sure.
And here you really want it to be base independent, so you should be able to change
Yeah,
anywhere.
yeah.
And then you really have to keep track of it.
So just wanted to make a remark to put a tie on the question I asked to the previous talk. So in that talk, tensors were always concrete and only tensor operations were shape inferred. So if we wanted to make shape inference for tensors themselves, then it becomes helpful to distinguish the input and output components.
Yeah.
Thank you.